Hello and welcome back to Junction Embedded. Today is the third class of embedded systems and I will discuss something about timers, and the application or the extension of timers is PWM, and the application of PWM is sound. As I shown you in the last class, we are generating some delay using the timer delay function, some 100 millisecond or 500 millisecond of delay. So that is achieved by timers. Let's see how the timer works inside a microcontroller. As I have told you already that microcontroller has so many peripherals inside, and timer peripheral is one of them. Last time we discussed about the GPIO peripheral. Today we are discussing about timers. Each circuit or each digital circuit needs some source, some clock to run, and this microcontroller also needs some clock. So there are internal clocks also, but there's provision of external clocks also. You will connect some crystal here, maybe of 12 megahertz or anything, and this clock will be fed to the clock generation module. There is one more peripheral, the PLL, the phase lock loop, which will generate some stable clock and maybe of higher range, let's say some 100 megahertz. This 100 megahertz again divided by some circuitry, some divider or multipliers to generate some peripheral clock. So the output of this divider circuitry is connected to this timer, and this is your peripheral clock provided to the timer. This type of clock generation is again very much architecture dependent, because there can be a single register to divide the clock for all the peripherals, or there can be separate registers dedicated to each peripheral. So there are some registers of this timer. Timer, as the name indicates, it provides some mechanism to calculate the system time, to calculate the counts of the clock provided to the timer. So for that purpose it uses a counter register, when to count, when not to count, or what is the reset value or the maximum value. Everything can be controlled from the control register, and then you have the prescaler register to increase or decrease the resolution. So I have taken some random configuration here. The peripheral clock frequency is 1 kilohertz as an example, and with 1 kilohertz you have 1 millisecond of time period. So this high and low constitutes 1 millisecond. Prescaler value will be used by the timer module to increment the timer counts, and the relation is like that. The timer will always wait for the PCLK pulses to increment by 1, but how many pulses does the timer need to wait for will be told by the prescaler value. In this case prescaler is 1, and timer will always wait for prescaler plus 1, that means 2 PCLK pulses to increment by 1. So the 2 pulses means one high, one low, and another high and low. Here is the end of 2 pulses, then again here, and initially the timer counter value is 0, but when it gets the first trigger it is incremented to 1, then again it increments to 2, then to 3. So like this it goes till the maximum value of that register. So if we are having a 1 byte of timer, that means maximum value is 255, and after 255 of counts it comes back to 0, and then again it starts counting. So it's like up counter which is reset after the maximum value. So what you have seen in this basic configuration, that you must have a peripheral clock to run the timer, then you must have a prescaler value, and the timer counter is the counter value which automatically increments when it gets those many peripheral clock pulses. So with 1 kilohertz you have 1 millisecond, and the 2 peripheral clock constitutes 1 timer count, so it is 2 millisecond, and this 2 millisecond is nothing but the resolution of the timer, which means that after every 2 milliseconds the counter will be incremented by 1. So this is how you can relate the counter value with the time. At any given point of time you can read the counter value, and after some time, if you want to know the time, you can again read the counter value, and you can take the difference of these two counter values to know the time difference. So for example, the counter was 60 at this instance and it was 10 here, so the difference is 50, and 50 multiplied by 2 is 100 millisecond. So that's how you generate the time using the counter values, taking the difference of the counter values. But with this configuration, you have a resolution of 2 millisecond, which means you cannot measure time less than that. So if you have to measure in milliseconds or in microsecond, 2 millisecond will not work for you. So you have to decrease the prescaler value. This is the one way you can do it. And by decreasing the prescaler value to 0, the rate of counter increment will become as same as the PCLK rate, which is 1 millisecond. And if you want to improve further, then you have to increase this the peripheral clock frequency. Maybe you can have 1 megahertz. With that you can generate microseconds and then constitute to some millisecond using the prescaler values. So that was very basic about the timers, and now we will discuss something about the PWM. So first of all, what is PWM? PWM stands for pulse width modulation. It's a technique in which you can increase or decrease the pulse width. So I have a configuration like, let's say this is 1 millisecond, and the on time and off time is actually same. So this is the first configuration. Another configuration is in which the on time is less than the off time. This is also 1 millisecond of time. And third configuration is when the on time is more than the off time. Basically, by varying the width, we are varying the duty cycle. Duty cycle is calculated as the on time divided by the total time period, which is nothing but the T on and T off. And by varying the duty cycle, you can actually control the average voltage, which is directly proportional to the duty cycle. So for example, if this maximum voltage is 5 volts and you are using 50% of duty cycle, the average voltage will be duty cycle into the maximum value. So duty cycle is 50%, maximum value is 5 volts, which will come as 2.5 volts. So exactly half of this one. So this is the significance of PWM duty cycle, that you can control the average voltage, and by controlling the average voltage you can actually control your system, maybe your motor or your sound or the intensity of the light, which we are going to see practically now. So to generate the PWM using a microcontroller, you have the timer counter register, which is incrementing from 0 to the maximum value. If it is a 16-bit register, the maximum values is FF and FF. And there is one more match register, which is accessible by user, which is writable by the user, the programmer. So you can write any value here, maybe something like that. And the internal circuitry of the timer module will compare this match register with timer counter register to generate the output. So this FF will be somewhere here, and this is again configurable, that when to generate a high output or when to generate a low output. And there can be a configuration like output high when match register is greater than TC and T. So we can follow this configuration in our example. So whenever match register is greater than the counter value, means this slot here the match register is FF, but the timer counter value is 0 to FF. So in this case the output will be high. So here I am drawing the timer output. So it's a high output because the timer value is less than the match register. Then the reverse of this is the counter value becomes greater than the match register, so the output will be low till this point. Again, the counter value is resetted to 0, which is again less than the match register, so the output will become high. So this way it is controlled, and by varying the contents of this match register, you can actually vary the pulse size. So here's my laptop, and let's open the datasheet of this microcontroller, and here's the Pwm chapter, and you can see a lot of registers here. So interrupt as of now I'm not using. So this is the control register using which we will be setting our PWM. This is the TCNT register, what I was talking about, the timer counter register. This is the pre-scaler register, and these are the match registers for each channel. So I have this template for PWM generation. So first of all, I can write the Pwm initialization code, in which I'll be initializing the pin for the PWM. So if you read the data sheet, you will come to know that PWM is available on which pin. So there's a PWM on port 021 pin, uh, then you have PWM here on port 09 and 8 pin. So there are 6 different channels for PWM. Depending on the connections, we will use the PWM channel. I have connected one LED on port 021 pin, which is the channel 5 output, PWM channel 5 output. So I'm going to use PWM channel number 5, which is port 021. So if you remember, we have to use pin cell 1 for port 021st pin, because pin cell 0 is for pin number 0 to pin number 15, and from pin number 16 to pin number 31 we have to use pin cell 1 register. So here is the pin, and if pin number 10 and 11 are 0 1, then that pin is configured as the PWM pin. So we can do this way. And next thing is pre-scaler. So based on my configuration, I have selected a prescale value of 15, which means after 15 PCLK pulses, the counter will be incremented by 1. So I have to keep a value 1 less than that, because the timer circuitry will add 1 to this register, and then it increments the counter. And next thing is match control register. So we can select which channel do we want to compare. Do we want to compare with the timer, and whether we want interrupt or not. This type of configuration can be selected using match control register. So PWM MCR, I will simply put as 1, which means I'm using channel 0 for resetting the counter. Then we can select the match register value. So for PWM generation, 2 channels are needed. I'll put some random value 100, in the MR0 and maybe 50 in the MR5 register. So whatever the value we keep in MR0, I'm just putting half of that in the MR5, which means I am trying to generate a 50% duty cycle. There's one more register which is latch enable register, because there is a concept of shadow register and latch register and output register. You can obviously read the data sheet to know more about these registers. I have something like PWM latch enable register. I will enable the latch for the 0th bit, means 0th channel, and the 5th bit, which is corresponding to the 5th channel. We can have one separate function for starting the PWM, in which we will be setting the PWM control register. There is one more register, PWM PCR, in which the channel output is enabled. This is the PCR register, and channel number 5 is on 13th bit, so we can enable the channel number 5. And we have one more register, the timer control register. You can see in the data sheet the timer control register TCR, which has only 3 bits in use. So when you want to enable the counter or disable the counter, and you want to reset the counter, and if you want the PWM mode, basically this PWM peripheral can behave as a normal timer also, so this bits puts this module into PWM mode. So we can just put simply 1 here, and we can enable the PWM mode. So at bit number 3, so we have configured the PWM and we have started the PWM also. What we can do is we can take some value, and this value is corresponding to the duty cycle, so it reaches 100, and this value will be used by the channel 5 for increasing or decreasing the duty cycle. And whenever the match register is updated, the latch should be enabled again, and with a timer delay of 10 milliseconds, and we should have this never ending loop so that it repeats this functionality. Now let us compile this file and download this to the controller. So that's how our PWM looks like in the form of light. You can control the intensity by increasing or decreasing the duty cycle. Now let's change one thing. We can copy this for loop in the reverse order. We can start from 100 and go to 0, and with decrementing, and rest of the things remain the same. Now let's compile this code and see the output. The intensity increases from 0 to 100, and from 100 to 0 it is again decreasing. As I told while initializing the PWM, that this MR0 is for frequency. This is the frequency selector and this is the width selector. So by varying the MR5 you can vary the width, and by varying the MR0 you can vary the frequency. Because sound is all about frequency, we the audible frequency is from 20 hertz to 20 kilohertz, so we will be generating some waveform within that range. I already have some values here, uh, so this value corresponds to the C note in the music, and this is according to my clock, according to my settings. This is the number. In your board, in your settings, this number will be definitely different. So I will be using this array for generating these notes, and this value I'll use as an index. And then you can increase this delay, because this is sound. At least 500 millisecond you should hear one note. So we can compile this file and we can So here's my setup. I have used one audio jack in parallel to this LED. So I'm directly supplying the PWM output to this audio jack, and this is my headphones jack, and this can be so that's how you generate the sound using PWM, using embedded systems. uh, these frequency table you can just multiply by 2 and the pitch will be lowered. So uh, what I can do is directly here, if you can multiply by 2, you will hear a lower pitch now. Okay, let's download this. And if you get enough time to play with the music notes, to play with the PWM, you can try something like that. You can compile this code and you can program it. So it's getting programmed now. uh, let's see the output, let's hear the output.